than where we are today, because where we are today is due to the fact that our teachers helped us to be where we are today, and let us pay our respects on this Teachers' Day. With that, I'll be really talking this morning. First of all, also I want to thank the IEEE Photonics Society chapter, and then OSA chapter for inviting me to participate in this LAMP talk series. And then it's a pleasure for me to be able to participate and interact with all of you. So today I'm going to really talk about semiconductor nanowires and nanostructures for optoelectronics applications. So as Kishore mentioned, that I'm from the Australian National University, but I also have got honorary appointments in various parts of the world. And so really, I want to really thank my colleagues in India, Japan, China, Taiwan, and then US and UK for inviting me to be part of their institutions in an honorary role. Before I proceed further, I would like to thank my collaborators, and this talk is really a collective effort between my group at the Australian National University and many groups in Australia, US, UK, China, and Sweden, Italy, Russia, Switzerland. So really, it's a collective effort with many colleagues, and I want to thank all my colleagues and collaborators, including many students and postdocs, those who contributed to our joint research. And without their contribution, there's nothing much to talk about. And also, the beauty of science is that there are no national boundaries. We can all work together. And then I've always enjoyed working with people from 30+ countries or so. And it's really an honor for me to be working with all my international colleagues and Australian colleagues as well. This is my group at the Australian National University. And so really typically 10 to 12 nationalities at any one time, and including many from India. And so really, it's a really bright young people, and it's really a pleasure to really work with all of them. And again, I want to thank them for their contributions to our research. And again, without their hard work, and there's nothing much to talk about. I also want to thank my colleagues, those who are in the group, and academic colleagues, and they are the ones, those who lead our research, and so work very closely with our students. And I want to thank them for the leadership as well. I also take this opportunity to thank our funding agencies for their support for our research. So here is an overview of my talk, and I'll give you the motivation why we're interested in nanowires and nanostructures, and I'll talk about how we grow these structures, and then talk about a wide variety of applications of these nanowires for various lasers and LEDs, Terahertz detectors, solar cells, and photoelectrochemical water splitting, and then even using these ones for neuron growth. And I'll draw some conclusions. Before I proceed further, I would like to thank many people, those who are working in the field of semiconductor nanowires and nanostructures in various parts of the world. And so really, we are enriched by other people's contribution in terms of science. And it's very important for us to really acknowledge people, those who have contributed to the research, which we are really building up upon, and without which, well, we will be poorer in terms of the progress which can make in science. So before I proceed about nanostructures and nanowires, and let's talk about the industrial revolutions. So as many of you know, that the first industrial revolution has started with the steam power and led to the mechanization. The second industrial revolution started with electrical power, led to the mass production. Third industrial revolution started with computer power and then led to automation. And fourth industrial revolution, people are predicting that the biological world and then the digital world will come together. Light is going to play an important role because of the fact that the light is used to sense and interface humans and machines. And in fact, we get about 80 to 90% of our information is obtained by light. So really, optical photonics and optics-based technologies are going to play a very important role. Currently, market size of these industries is about 1 trillion Australian dollars, or about 700 billion American dollars. And so then people are predicting by 2030, this industry or the market size will be doubling, indicating that the photonics-based technologies are going to play an important role in the future. So the World Economic Forum has identified the technologies needed for the future. And so then they've the holographic display, they've identified various technologies. These include holographic displays, and which could be holograms coming out of your phones, for example, to be able to give a three-dimensional image of the people whom you're interacting with, and particularly your families, for example. And then wearable optical sensors, which are able to monitor your well-being continuously. And then also light navigation and communication and LiDAR technologies, for example, for autonomous vehicles, and 3D vision and gesture recognition, and enhanced machine vision and augmented reality. These aspirational technologies require fundamentally new approaches for smart and miniaturized optical systems. And in fact, that's what precisely we are trying to develop as part of a new Center of Excellence funded by the Australian Research Council on Transformative Meta-Optical Systems, TMOS, and so working with many colleagues in various parts of the world. And in this Center of Excellence, and we are really focusing on active meta-optics using the nanostructures to be able to generate light, for example, lasers and LEDs based on nanostructures, which I plan to cover, and then also manipulation of light using metamaterials, and then detection of light again using nanostructures. And so really we are trying to understand the light matter interaction at the nanoscale and to be able to generate and manipulate and detect light. The Center of Excellence is directed by my colleague, Professor Dragomir, and we got about 15 CIs, chief investigators from 5 different universities in Australia, and about 15 partner investigators from various parts of the world, including Caltech and Oxford and Cambridge and various places. And also many associate investigators are also involved in this one. So now let me move towards optoelectronics. And I mentioned about optoelectronics. What is optoelectronics? Well, all of us know about electronics, and then the electronics, we have been using silicon as a workhorse for electronics, and whether you're using any computer or any smart device, electronics is most likely made out of silicon, for example. But in the case of optoelectronics, we are converting electricity into light, like LEDs and lasers, and conversion of light into electricity in using photodetectors, for example, and solar cells as well. So just that's what is optoelectronics: conversion of electricity into light, or conversion of light into electricity. And then typical optoelectronic devices are lasers and LEDs and photodetectors, solar cells. And so really, it turns out, though silicon is an excellent semiconductor for electronics applications, it is not a very good light emitter. Still, silicon is also nowadays used for lots of silicon photonics applications. And Professor Shankar Sauraja has given a talk earlier to you. But unfortunately, silicon being an indirect bandgap semiconductor, it cannot emit light. If you want to really get efficient light emission, and you need to use direct bandgap semiconductors, which are made out of these 3,5 compound semiconductors of gallium arsenide, group 3 and group 5 of the periodic table, and indium phosphide, gallium antimonide, gallium nitride, aluminum nitride, indium nitride, combination of these materials. And these materials have got a different band gaps. The energy difference between the bottom of the conduction band and the top of the valence band. And then these different materials have got different band gaps. So that means they'll be emitting different colors of light, or otherwise they're absorbing different colors of light, for example. So in fact, the developments in the nitride technology in the 90s or so has led to the development of the blue LED, which was a missing link. Till that point, we had red LEDs and then the green LEDs made out of the other semiconductors, but blue was a missing link. And due to the development of this blue LED has led to the white LEDs, and nowadays LED lamps have been developed because of the fact that the developments in the nitride semiconductors that led to Nobel Prize in Physics for these Japanese scientists, Dr. Amano, Dr. Nakasaki, and Dr. Nakamura for physics in 2014, which has really revolutionized in terms of energy consumption has come down quite significantly by using LED lights, and also these LED lights last for a long time. We call this thing as something called solid state lighting. But also nowadays large area displays, and then again made out of these LEDs, because these LEDs are very, very bright. The same materials which are made for making LEDs can also be used for making lasers. And so again, these lasers, and of course you cannot imagine a modern life without lasers, for example, here. And just to give one example here, then today I'm able to talk to you because of internet. So in the internet very much depends on optical fiber communications. So the electrical signals from my computer are been translated into optical signals using lasers, and they're modulated. Essentially, a modulator is nothing but an on-off switch. And then you end up sending this one through optical fibers. And then in between, you end up having some optical amplifiers so that you can be able to amplify the signals. And on the other end, you're able to convert these optical signals into electrical signals using photodetectors. So as you can see that the lasers and photodetectors are used every day, every time, whenever you're using internet, for example. And so in addition to light emission, and then the same semiconductors could also be used for light detection. For example, some of these materials are used for infrared detection and light detection. For example, you can use it for night vision applications, biomedical imaging applications, or even looking at the heat generation in the computer chips while you're operating them, so that you can be able to redesign the computer chips so that you can redistribute the heat. So because heat dissipation is a major issue nowadays in the computer chips, where we are packing billions and billions of transistors. But also nowadays, the most efficient solar cells are made out of these 3-5 semiconductors, though silicon is workhorse for the solar industry. But multi-junction solar cells made out of 3-5 semiconductors, you can really reach to the now 47 to 48% efficient solar cells. And these solar cells have been developed for space applications, and generally these are expensive. But since the satellites, satellites are so expensive, you want to have the most efficient solar cells. But also these solar cells made out of 3-5 semiconductors are also radiation hard. That means in the space, when you got a lot of cosmic rays and others are really hitting these solar cells, they'll be able to last much longer period than silicon solar cells, for example. So once the efficiency has exceeded more than 40%, and people started thinking about where can I make use of these solar cells in the terrestrial applications. But as I told you, these solar cells are expensive, unlike silicon. And that's where people have been trying to use these ones for so-called concentrated photovoltaic systems, where they use this, the solar dish, essentially parabolic mirrors, and they are really focusing the light to the central, this focal point here. And then you really can be able to generate 500 to 1,000 suns of intensity of light there. So people want to make use of these most efficient solar cells because the system cost is so high. Also, they are tracking the sunlight as well. So that's where 3-5 semiconductors have been exposed as a concentrated photovoltaic systems. For example, you've got a remote village. Instead of really transporting the electricity to remote villages, you can really be able to put some of these dishes and then be able to charge these, charge the batteries using these solar concentrated systems. So thereby you'll be able to provide the electricity and then other electrical needs for the local population, for example. Because the transmission losses are a major issue whenever we're dealing with in terms of electricity, for example. So the nanowires I was talking about, and nanowires. Why nanowires are people are so much interested in? Nanowires are seen as building blocks for the electronics and for next generation electronics and photonics. One of the unique things with the nanowires is the lattice mismatches are no longer an issue. So whenever you talk about crystals, whether it is silicon wafers for the electronics or 3-5 semiconductor wafers for optoelectronics or photonics, and then you're using single crystals of these materials, and then typically, and then also you got something called a unit cell. Essentially, the lattice constant is the size of the unit cell which repeats itself in the crystal, for example, in all 3 dimensions. So whenever you're dealing with the 2-dimensional materials, you always have to worry about what is the layer lattice constant with respect to the substrate constant. And then also you end up having these materials initially strain, and above certain thickness, they start dislocating and then creating defects. And then those defected materials are useless as far as optoelectronic devices are concerned. In the case of nanowires, and because of their nanoscale and 3-dimensional architecture, if you got a material which got a large lattice constant with respect to the substrate, and can expand without creating any dislocations. And if you got a smaller lattice constant material, it can contract without creating any dislocations. So that means, in principle, we should be able to really grow nanowires of any material on any substrates, for example. We can also create axial heterostructures. You can see this green material is different than the red material. You can create the quantum dishes or quantum disks or quantum dots, for example, in the nanowire. You can also dope these nanowires p-type and n-type so that you can create p-n junctions. And you can also create a core shell nanowires. And this pink material is different than the red material, for example, here. Also, you can create the branch nanowires. So they really provide a wide variety of 3-dimensional architectures, for example, here. So really, just to give you some examples from my own laboratory, where we have shown gallium antimonide can be grown on top of gallium arsenide despite large lattice mismatch. And then we were able to show that we can get atomically perfect gallium antimonide because gallium antimonide is a very good infrared detector material. You can also grow indium arsenide. Indium arsenide is a very good material for transistors, and also these you can grow cantilevers on top of this gallium arsenide stem here. They could be used for scanning probes and thirst applications or so. You can also create things like indium phosphide nano trees, which are very good for energy harvesting applications, like splitting of water to generate hydrogen, for example, which I will come back to. And then also recently we started moving from nanowires into nanomembranes. Again, I'll come back and then talk about it. As you can see, that these nanowires can play a very important role in a wide variety of applications like LEDs, lasers, photodetectors, and biosensors and solar cells. But also it turns out that these nanowires are also seen as important technology requirement for the International Technology Roadmap for Semiconductors, those who also identify what technologies they need for electronics. They've identified the nanowires are also going to play an important role in next generation electronics. Instead of having transistors in the lateral direction, you can have transistors in the vertical direction so that you'll be able to pack more transistors. But also these 3-5 semiconductors, not only the direct band gap semiconductors, they also got a higher carrier mobility. So that means faster transistors, 3-5 semiconductors are better, but the lattice mismatch has been limiting us, but now lattice mismatch is no longer an issue. In fact, we can be able to make 3-5 nanowires on silicon. In fact, recently IBM has demonstrated indium gallium arsenide nanowire transistors on 6-inch wafers of silicon and showing excellent performance, indicating that the future is looking very bright, both for electronics and photonics, for example. So let me see why. Okay. So now, if the nanowires are so much of importance, and how do we make these nanowires? So there are two main techniques which we use. One is called as metal catalyzed BLS growth process, vapor liquid solid growth mechanism. Another technique is called selective epitaxy. Okay. So then I'll just come back and tell you a little bit about it. They're also using something called MOCVD, metal organic chemical vapor deposition. There's also an alternative technique called molecular beam epitaxy. And you can use either of the techniques to be able to make the nanowires, and it's a choice of yours because MOCVD is widely used in the industry. For example, nowadays MOCVD reactors are used to make large number of solar cells, the LEDs or lasers, any optoelectronic devices, for example, including solar cells as well, 3-5 solar cells. And so that's why we have chosen MOCVD technique, and so to cover a broad spectrum of 3-5 semiconductors. So in this case, we take a semiconductor substrate, and I'm giving an example of gallium arsenide substrate, and then put some gold nanoparticles, and then typically about 30 or 50 nanometers in diameter. You can buy these gold nanoparticles in a colloidal solutions these days from 5 nanometers up to 300 nanometers or so. So really these, because they're used for biological tagging applications. So we put a droplet of this colloidal solution of gold nanoparticles, and then we put this one into the MOCVD reactor, and then heat it up to somewhere between 370 to 500 degrees Celsius. The gold typically has got a melting temperature of more than 1000 degrees Celsius. But whereas if you really react the gold with gallium or aluminum or indium, what happens is that the alloy of the gold gallium, for example, has got a melting temperature as small as 350 degrees Celsius. Same with indium, gallium indium or gallium aluminum as well. So now you can see that if you put this one into the MOCVD reactor and heat it up, and then even at you can start to essentially create this gold gallium eutectic liquid, and then if you introduce the gases needed for the growth of gallium arsenide nanowires, for example, these nanowires, these gases get incorporated in liquid alloy, it gets supersaturated, crystals start splitting out, and gold is always sitting on the top here, for example. This is the work of my former student, Dr. Hannah Joyce, who is now an associate professor at Cambridge University. During her PhD at the ANU, she really developed these gallium arsenide nanowires and demonstrated excellent performance gallium arsenide nanowires, which are cylindrically shaped and also with no defects whatsoever here. For example, here is a scanning electron microscope image. You can see the gold nanoparticle at the top, and you can see the transmission electron microscope image showing this nice gold nanoparticle, and then the gallium arsenide nanowire showing atomically perfect nanowires, for example, here. So really, you can see that the diameter of the nanowire is very much dependent on the diameter of the nanoparticle which you're using. So we made the nanowires which are as small as 10 nanometers in diameter and then as big as 300 nanometers. We choose the diameter of the nanowires depending on the applications which you really particularly have got, which I will come back to. And the second technique called selective epitaxy. In this case, we don't use any metal nanoparticles, and sometimes you don't want to use metal nanoparticles. So in this case, what you do is that you put some silicon dioxide by plasma enhanced chemical vapor deposition or PECVD, and then put some photoresist or electron photoresist, and then create the patterns of the structures of the holes, for example. And then you transfer those patterns through silicon dioxide so that silicon dioxide is everywhere in these holes. Indium phosphide is exposed. I'm using indium phosphide, for example, in this case. It could be any semiconductor you want to choose. So then you put this one into MOCVD reactor, heat it somewhere between 650 to 750 degrees Celsius, and then introduce the gases needed for the growth of indium phosphide, trimethyl indium and phosphine. And these gases dissociate, and then you really nanowires are grown in these holes because that's where the nucleation of this crystal starts taking place, for example. Here. Because we created these ordered patterns of the holes here, you can see also ordered patterns of these indium phosphide nanowires. And you can see the top view of this one. You can see beautiful hexagonal facets because these nanowires are growing along 111 crystallographic orientation because we're using the 111 crystallographic orientation substrates because that's the lowest surface energy orientation. That's why these crystals like to go in the particular crystallographic orientation. This is a work of my former student, Dr. Chian Gao, and then who is now a research engineer at the Blue Glass, a company which is trying to make LEDs glass substrates, for example. But again, we made the nanowires which are as small as 70 nanometers using this technique and as big as 700 nanometers. And again, depending on the applications, you choose the right kind of diameter of the nanowire. So we've taken these nanowires and looked at the light emission. So we've excited these nanowires with the laser pulse, and you generate something called electron hole pairs, and essentially exciting the electrons from the valence band to the conduction band, and then they fall down and emitting light, for example. So then we quantify the quantum efficiency of the light emission as a function of the excitation power of the laser. You can see that this blue curve, the red curve showing that the nanowires have got about 50% quantum efficiency depending on the excitation power, for example. But whereas we also compare this one with the epitaxial layers, which are the two-dimensional layers which we grow, and you can see the blue curve, and then they are very much comparable, indicating that the surface non-rate recombination is not a major issue in the case of indium phosphide nanowires. And then you can really get excellent performance in indium phosphide nanowires, which are very good for making lasers and LEDs and solar cells, and which I will come back to. But that's not the case with all the semiconductors because of the large surface area of these nanostructures. For example, gallium arsenide has got a very large surface recombination velocity. You end up really getting very low quantum efficiencies, unless otherwise you do some surface passivation, which I will not have time to go into the details of that one, which I can come back and then share a little bit with you later. So now let me move towards from the nanowires to other structures. So I told you that we are opening a hole in this silicon dioxide mask and then able to grow the nanowires, which I've already shown you. But we asked ourselves, instead of opening a hole, what will happen if you open a slot or a ring? What type of structures you can be able to get? This is a work of my student, Dr. Nain Wong, and then he's now a postdoctoral fellow in the group now. Okay. So then again, he takes this indium phosphide substrates, deposits some silicon dioxide or silicon nitride by plasma enhanced chemical vapor deposition, and then put some photoresist and do electron lithography and create these different kinds of patterns. And then you put this into the MOCVD reactor and then grow these structures. And then again, he spent a lot of time, about a 4-year period, in optimizing various growth conditions in order to be able to look at what the best quality nanostructures you can be able to get from these structures. So you can see that if you open a slot along a particular crystallographic orientation of 101 bar, you put this in an MOCVD reactor and then heat it up to somewhere between 650 to 750 degrees Celsius, and then introduce the gases near the growth of indium phosphide. You can see you can get a beautiful nanomembranes, for example, and with these particular facets on the side walls here, for example. But if you open the slot along another crystallographic orientation, and again, also you can get the nanomembranes, but these membranes are a bit thicker because there's some sort of a lateral growth is taking place. Also, they end up having a different kind of facets than this one particular, for example, here. But then if you open the slot in between these two, So now you can see you can get a beautiful diamond-like structures with these alternating facets of these two types of facets. So now you can see that instead of just making nanowires, we're able to make thick membranes and thin membranes, thin membranes and thick membranes and diamond-like structures. It really opens up lots of opportunities. In fact, we have used these nanomembranes and demonstrated some nanowire transistors in collaboration with Professor Adam McLeich's group at University of New South Wales, for example. Okay. So really, people have demonstrated also nanowire transistors as well, but I will not be focusing on the transistors in this particular talk because the talk is really focused on optoelectronics. So then let's go and look at the nano rings, for example. We open the rings, what will happen? You can see that you can get these beautiful ring-like structures, again with alternating facets of these two types of facets, which I've shown you here. Again, Nine Wong spent a lot of time in optimizing the growth temperature and then also size of these nano rings and all these sorts of things, which I will not have time to go to the details of it. So if you keep on growing, then it really gets filled up, and you can see the nanomembrane here again, and which is in the flatter direction, the horizontal direction, the vertical direction, which I've shown you earlier. And it finishes off if you keep on growing with these beautiful hexagonally faceted structures, again, because of the low energy facets being 110 facets, which the crystals like to be in the low energy facets whenever you go. So Nine Wong has taken these nanostructures of nanomembranes and nanodiamonds and nanorings as a top view of the electron microscope image. And then here is it, cathodoluminescence. Instead of using lasers to excite electron hole pairs, and then in this case, what we do is that we use electron beams in a scanning electron microscope, and then excite these nanostructures and look at the light coming out of these ones. Essentially, again, exciting the electrons from the valence band to the conduction band and looking at the light coming out of these ones. So then the electrons are falling down from the conduction band to the valence band, for example. You can see the bright light emission and then also very uniform light emission, indicating that these are really excellent structures. And so then, Nine Wong's 4 years of hard work has really paid off. And these sorts of structures are very useful for making quite a variety of optical devices. For example, we are looking at the ring resonator lasers, which I'll come back and then share with you. Okay. So in terms of now you can see that we can make nanowires, we can make nano membranes, nanodiamonds, and nano rings. There's no limit in terms of what type of structures we can be able to make. So now, till now, I've only spoken about materials. Now let me move towards devices. So in terms of lasers, all of us have studied about lasers. And so we've been told that you need to have a gain medium. You need to create an optical cavity, putting some mirrors here, right? And you pump this one so that you're creating population inversion. And then as and when the gain is equivalent to the optical losses in the cavity, then the lasing starts taking place. So here is a lasing threshold condition. Essentially what it says is gain need to be equal to the internal optical losses or absorption losses or scattering losses, and then the mirror losses. And that's what essentially this one is saying. It also depends on the length of the cavity as well. So this is an undergraduate optics course, we all learned about it. But if you take the nanowires and if you excite the light from the top, and then what happens if the light starts propagating along the nanowire, because nanowire, if you design correctly, it acts like a waveguide, because nanowire has got a refractive index of 3.4, and then this, because particular semiconductor which we're using, and surrounding medium has got a refractive index of 1, air or vacuum, for example. So now that means you'll be able to really excite the light and then be able to use this as a waveguide, and both ends of the nanowire act like mirrors because of the refractive index difference between the nanowire and then the surrounding medium. So now you can see suddenly, if I get the nanowire designed right and good quality nanowires, each nanowire should act like a laser, without having to put any mirrors or creating any other further cavities and all this stuff. Okay. If you pump these nanowires, and also you can create population inversion, and then you'll be able to really get excellent performing nanowire lasers. And that's what our aim has been. Because these are 3-5 semiconductors, and so then because they are direct band gap semiconductors, they also got a very good gain as well. So they act like a gain medium. They also act like a laser cavity, for example. So we've been working on this, making wide variety of nanowire lasers. And in fact, this work has been really led by my colleague, Dr. Sudha Mokapati, my former student, and then now she's an associate professor at Monash University in Melbourne, which is leading her own research group now. So we've demonstrated, in fact, the world's first gallium arsenide nanowire lasers. This is the work of Dr. Dhruv Saxena, who is at Imperial College now. And then Woodside indium phosphide nanowire lasers, Dr. Chian Gao, whom I mentioned about at Blue Glass. And again, Dr. Saxena has also demonstrated quantum well nanowire lasers. And then Dr. Tim Burgess has demonstrated zinc-doped gallium arsenide nanowire lasers with high efficiency as well. I'll not really have time to talk about all the details of all these lasers, and in fact, we publish this work. And I'm going to give you one or two examples of these ones, for example. So the first thing what Dhruv Saxena has done is that he has done some simulations of how the light is propagating to these nanowires using something called FDTD simulations, finite difference time domain simulations. You can also use a finite element simulations as well. And so he looks at, how the light is propagating through a 260 nanometer gallium arsenide nanowire, which is a TM01 mode, which has got the highest field at the core of the nanowire, and T01, which has got the donut-like shaped field distribution, HE0, HE11, HE21, EH11. So the higher order modes and others also he looks at. So here is a case of how the TM01 mode is propagating this particular nanowire of gallium arsenide, for example, here. So then what he does is that he plots the threshold gain, how much gain is needed in these nanowires in order to be able to get the lasing to take place as a function of the diameter of the nanowire for a fixed length of about 10 micron long nanowire, for example, here. So as you can see that the threshold, the gain is required is dependent on the diameter of the nanowire. It also varies for the particular mode. And then you have to choose the right diameter of these nanowires. You can see that the typically 250 to 300 nanometer diameter nanowires have got the lowest threshold gain for lasing, for example, for these particular modes, for example, here. But if you really go and look at this one, you can see that we are starting not from 0, starting from 150. If you go to smaller diameter nanowires, like 50 nanometers or 30 nanometers, threshold gain for lasing required is so high, before you can get any lasing, the nanowires gets damaged because it's exceeding the damage threshold of the material which you're using, for example, here. So that's why instead of using 30 or 50 nanometer nanowires, and we had to go for 260 nanometer nanowires of gallium arsenide, and we had to coat this one with the aluminum gallium arsenide, which has got a larger band gap material to suppress the surface non-rate recombination, for example. Okay. So this is again, we transfer these nanowires onto glass substrate because glass typically has got a refractive index of 1.4. So that means light is confined to the nanowire, which has got a refractive index of 3.4 or so. Again, he calculated peak gain as a function of the injected carrier density, and you can see this threshold-like behavior. And then it's also, above this point, it starts lasing. And again, it also depends on the temperature at which you're operating this one. The higher the temperature of the device, and higher the amount of carriers you need to inject in order to be able to get the losses, get over the losses which you got in the nanowire cavity, for example. Here. So again, to cut the long story short, and based on Dhruv Saxena's design, and during his PhD, and my other student, Dr. Jenny Jiang, Nain Jiang, who is now a postdoc at Cambridge University, she has grown this gallium arsenide, aluminum gallium arsenide core shell nanowires. They're about 6 microns long in length, transfer them onto a glass slide, and Dhruv Saxena did these measurements. You can see if you start pumping these nanowires, and below threshold, you see a broad light emission, like a spontaneous emission, or like a light emitting diode. And then above threshold, you see a very sharp light emission, and like a stimulated emission, and a coherent light is coming from a particular narrow wavelength of light here, for example. We can look at the output power versus pump intensity. You can again see this threshold-like behavior, a log plot showing the S-type behavior, showing that really this two lasing is taking place here. You can also see the beautiful interference fringes whenever the lasers are really operating. These nanowires are acting in the lasing mode rather than the broad LED mode, for example. You can he also did the simulations and then try to compare the interference fringes with the ones which he has measured, and they're very much comparable. These are the first room temperature operating nanowire lasers, gallium arsenide nanowire lasers, optically pumped nanowire lasers, for example, here. And this work was then published about 8 years back or so, for example. These are some of the smallest lasers in the world. And just to give an idea that I can put about 20 lasers within the width of your hair, and particularly along the length. And so of course, along the width, you could put a much more larger number of lasers, 3,000 lasers or so. So really, these tiny lasers. Why are we interested in tiny lasers? Smaller the laser, you consume less energy. Smaller the laser, you can pack more lasers in a particular area. And also smaller the laser, you also able to switch it on and off faster. So that means you'll be able to use it for fast optical devices for a wide variety of applications, like including communications. So that's why we're interested in these particular ones. So what are we doing with these lasers? And then, in fact, this is a technique which has been developed by my colleagues at University of Strathclyde, Professor Martin Dawson and Professor Michael Stein and Professor Antonio Hurtado. They developed a technique called nanoscale transfer printing. So they come up with a TDMS stamp, and then they can pick up the nanowire and then be able to drop it wherever you want, precisely nanoscale location of these ones, for example. This is the work, actually a lot of work has been done by research fellow in their group, Dr. Ben Hayward. And so his effort really helped us to be able to really make these ones, and followed by many students as well. So here's a case where we managed to transfer these nanowires onto flexible glass substrate, because we want to use them for flexible photonics applications or flexible optoelectronics applications. Because a flexible glass means you'll be able to bend it, and then you can also transfer it onto polymer materials or so. You can see these nanowires in optical image of these ones. You pump these ones, and you can see the light is coming from the both ends of the nanowires. You can see threshold output power in the light intensity versus the excitation power. You can see threshold-like behavior beautifully here. The lasing is taking place, and also narrow line width, indicating that, despite the fact that we did this nanoscale transfer printing, all the lasers or all the nanowires are lasing, indicating that this nanoscale transfer printing process is a gentle process. And so that means you can transfer them onto any substrate you feel like you would like to have, because glass is generally harder than the polymer materials, for example. So here is a case where we transferred on these nanowires in front of this Y junction, which is a SU8 based polymer waveguide, and then be able to put two nanowires and excite them, and then essentially two lasers coupling the light through this Y junction so that they could be used for routing and guiding of light for integrated nanowire lasers, particularly for multiplexing and demultiplexing applications, for example. This is the work of Mr. Dimitar Yautiks, and then he's really demonstrated these ones again on the polymer materials so that they could be used for polymer photonics applications, for example. So then we asked them, can you be able to really locate these nanowires into these nano antennas? So the nano antennas, and in fact, this is the work of my young colleague, Professor Fang Ren. Now she was in my group as the young scientist, but now she's gone back to China in Nanjing University. So she's been making these nano antennas as a terahertz metamaterials. And then these nano antennas, these so-called bullseye antennas made out of this aluminum metal. There was a gap in the middle, and we requested our colleagues in Strathclyde, can you be able to locate these nanowires in this gap in this nano antennas here? You can see the close-up of this particular one here. Here is nano antenna, and then the nanowire is in the middle here, with the gap where there was a gap. So when you do not have any nano antenna, as I told you, that light is coming from the both ends of the nanowire, like here, because nanowire act like a fabric cavity. But once you've got a nano antenna, light gets directed, and suddenly light is coming from the vertical direction in the middle of the nanowire here, for example. You can see the again threshold-like behavior, narrow line width, showing that we're able to demonstrate combining the nanowires and nano antennas, we're able to really create vertical emitting nanowire lasers. So whenever you want to couple the light to an optical waveguide, you make use of these edge-emitting lasers, which are fabric cavity. And whenever you want to have the light to be coming from the surface of the substrate, for example, and then you make use of these nano antenna coupled nanowires, so thereby you can use them vertically emitting lasers. For example, if you want to use it for meta-optics applications, you want to have coherent light sources, or even facial recognition applications. And there's those of you who may be using some of the Apple phones and others, there's a facial recognition system, and they're made out of the vertical cavity surface emitting lasers. By using vertical emitting nanowire lasers, our hope is that you'll be able to use very limited space, also consume less energy. That means your battery can last for a longer period as well. Okay. Again, this work has been published about 3 years back or so. This again drew considerable amount of attention from the global community. Again, these are made operating at room temperature. It's very important to make sure that if you want to use them for applications, you really need to use them at the room, show them at the room temperature operation. So now let me move towards ring resonators. I was mentioning to you this work of my student, Wei Wong. And then, as I mentioned to you, we were able to make the rings. And again, we can see this one is a ring. And then essentially, ring resonators, you end up having the spring gallery modes instead of having the fabric ferro modes, for example, here. So you can see that based on the design of Wei Wong, and so he has done extensive simulations of what should be the diameter of this ring and what should be the width of this ring. And then he has grown these structures using MOCVD. And then he's gone and then try to study these ones. You can see when you do not, if you start pumping, and when it is below threshold, you see a broad light emission, and above threshold in this region, and you see a very beautiful these interference fringes are coming from these whispering gallery modes. And then, in fact, he's compared these ones with the FDTD simulations, and they are very much comparable. And in fact, this work has just been published earlier this year in Nanoletters or so. Again, S-type behavior of the log-log plot showing and threshold-like behavior showing these things, narrow line width as well. Broad light emission, the broader, below threshold, a sharp light emission above threshold as well. So again, these are single mode lasing of the ring resonator lasers operating at room temperature as well. So now you can see these are the first bottom-up nano ring resonators, because most of the work which has been done earlier, they've always been done using the top-down approaches, but having these bottom-up approaches allows you to be able to make wide variety of ring structures and coupled ring cavities and all sorts of exotic stuff, which we are exploring and working on it. So till now, I have shown you only optically pumped lasers, whether it is nanowire lasers or ring resonator lasers, they're all optically pumped. So in order to get a laser, I'm using another laser to be able to pump these structures, for example. But ultimately, industry is interested in making electrical injected nanowire lasers, for example, or nanostructure lasers. So this is work of Dr. In Soo Kang, and then during his PhD, he is now at Samsung in Korea. And so during their PhD, he explored this possibility of making the electrical injected nanowire lasers. And as I mentioned to you, you need to dope these ones with PN junction to be able to inject carriers into these nanowires. He doped this indium phosphide in this green region with the zinc dope. Zinc doping creates P-type indium phosphide, and grown this indium gallium arsenide quantum well. Indium gallium arsenide is smaller band gap than indium phosphide. That means you're able to relieve this yellow one here, and that acts like an active medium. And then he has grown this N-type indium phosphide, which is doped with silicon. That means it gives N-type indium phosphide here, for example. He took about 2 years in order to be able to optimize these growth conditions, in order to be able to get a good quality quantum wells and good quality P-type and N-type doping and all these things. Here. You can see that here is a case of this schematic, and then his actual device here, and then they're scanning rectal microscope image, and then this P-type region here, N-type region here. He does electron beam lithography and would deposit some metal contacts and other things and patterning or so. Put some gold titanium contacts on both sides, and so that we'll be able to make electrical connections and be able to inject current and look at the voltage drop across them. So you can see the IV characteristics showing, and then nice, beautiful diode-like structure showing that the In-Sook's hard work paid off, and then he's able to demonstrate nice PN junctions, and also that may be able to make nice ohmic contacts as well. So then he looks at the light emission as a function of injected current. You can see that as and when you're injecting, the amount of current is increasing, and the light emission intensity is increasing as well. And also you see two emission peaks, and that's because of the fact that the quantum well thickness on top, this actual quantum well, has got a different thickness on composition with respect to the lateral quantum well here. So that's why you end up having two emission peaks. And these emission peaks are also in the 1.3, 1.55 micron window region. That's the region where the optical fiber communications are most efficient because of the low absorption and the dispersion, for example. But you see that light intensity is increasing, but there's no narrowing of the line width is taking place. That's what you typically expect from a laser, for example. You also don't see any threshold-like behavior, for example, light output versus the injected current, for example. So indicating that these devices are acting like a nanowire light emitting diodes, like a spontaneous emission, but not like a stimulated emission like a laser. So you ask the question, why? What is the reason for that? Because you got the nice nanowire, you made the PN junctions, you got the gain medium, why, what's the problem? It turns out when you put these metals have got, you've got a very high absorption, they create a very lossy cavity. So this, because of the lossy cavity, you pump them harder, you generate more heat, That means the gain peak comes down and you have to pump them harder, it becomes like a vicious cycle. So now Nikita Gagrani, who came from IIT Kharagpur, who is now working on trying to see whether she can be able to really get over this one, replacing these metals with some conducting, transparent conducting oxides like indium tin oxide, zinc oxide, and tin oxide or so, and then see whether we'll be able to really get over this problem and be able to make nanowire lasers, electrical injection nanowire lasers. It's been a very, very difficult problem. And Nikita has been working for the last 4 years or so. We still haven't been able to demonstrate these electrical injected nanowire lasers. And I hope next year or so, I will be able to really solve this particular problem. Before leaving, instead of using single nanowires, and then he's looked at this array of nanowires which are grown on indium phosphide, for example, here, and then making contacts to these vertically standing nanowires. How do you make contacts? Because it's very challenging. So he fills the gap in these nanowires with a polymer material like PDMS or BCB, and selectively etches the polymer material using the plasma etching and the plasma reactive etching, expose the tips of the nanowires, and then deposit some indium tin oxide, which acts like a transparent conducting oxide, put some metal contacts at the top and the bottom, and then injects current and look at the light emission. We can see the IV characteristics showing that he is able to get a nice diode-like behavior. And again, as and when you're injecting more and more current, and he is able to show that the light emission is increasing, intensity is increasing as a function of the injected current. And in fact, you can see below the probe here, and you can see a bright light emission from these devices, for example. Here. So why are we interested in this particular nanowire LEDs? But it turns out because we are embedding these nanowires in a polymer material, you'll be able to peel these things off. They could be used for flexible LEDs. For example, people are interested like Samsung and Apple and others, flexible displays for flexible foldable phones and foldable computers also. So really that's why INSUK has really focused quite a bit on in terms of being able to make these the polymer embedded nanowire LED arrays also, which is something which is worthwhile to really continue to pursue this once again. So until now, I've only spoken about nanowire LEDs and lasers or so. Let me now move towards the terahertz radiation. As many of you might have heard about terahertz radiation. Terahertz radiation really comes between the electronics and the microwaves and millimeter waves and photonics, where you talk about ultraviolet light, visible light, and infrared light. There was a gap called terahertz gap for many years. And then only during the last 20, 25 years, and we and many groups have been working in developing terahertz sources and detectors which are compact. And in fact, this now terahertz technology is widely used for a wide variety of applications. So why people are interested in terahertz radiation? It turns out that many biological molecules and chemical molecules have got signatures in the terahertz parts of the electromagnetic spectrum. So here is a case of the lactose, for example, monohydrate, anhydrate, and all these ones have got the signatures in the terahertz parts of the electromagnetic spectrum. Terahertz also a lot of pharmaceutical molecules, drugs, for example, are also have got signatures in this particular area, for example. Also, terahertz radiation is reflected by metals. So in fact, nowadays, if you go to the airport, they don't use X-rays because X-rays are ionizing radiation. They can create damage to your DNA. But terahertz radiation is a non-ionizing radiation because it's got a low photon energy. 1 terahertz is about 300 microns in wavelength. Okay? So that means, nowadays in the airports, if you really go to this, cube-like structure which you go through, and then that's where the terahertz detection is used for being able to detect any metal objects, for example. These can also be used for, biomedical imaging applications of looking at the cavities in the teeth, and wireless communications where you can download lots of information using from a kiosk onto a smart device, for example. Also detection of the water content in leaves so that you would water the crops only when they're needed rather than wasting precious resources like water. And this work jointly with my colleagues at Oxford University, Professor Michael Johnston group and Professor Laura Hertz's group. And we were developing some terahertz detectors using nanowires. And also there's work of Dr. Kun Pang, who did a PhD at the ANU, and now she's a postdoc at Oxford University in Professor Michael Johnston and Professor Laura Hertz's groups. So what we do, Kun Pang has done is that she has really taken one of the nanowires, and then she transferred onto a quartz substrate. Quartz is transferred to the terahertz radiation, and then try to make contacts using electron magnetography, for example, here. So then she comes with a laser pulse to excite the photocarriers in these nanowires, And then you come with the terahertz pulse. Electric field of the terahertz pulse is separates these carriers between these two contacts. We measure the photocurrent as a function of time here, for example. Okay. So you can see that the time scales we're dealing with is picoseconds, or this is a terahertz pulse, for example. That's what the time scales, the frequency of the time scale is typically about picoseconds or so. So now you can see if you measure the current as a function of time, that's what we're measuring here. You can extract the electric field of the terahertz pulse as a function of time and also measure the conductivity of the material which you're using here as well. In fact, that's what we were doing initially. We were using this terahertz spectroscopy to measure the electrical conductivity of the nanowires in a non-contact way of ensembles of nanowires. That's where we got the idea, how about using a single nanowire and then be able to make terahertz detectors, for example. Again, to cut the long story short, and then Kunpeng has demonstrated single nanowire gallium arsenide terahertz detectors, and then she extended that work to indium phosphide terahertz detectors, and most recently, she's been really developing these so-called polarization resolved terahertz detectors. So what we do is that we take the she takes the nanowires and then makes these antennas of these bow tie antennas. And it turns out that the antenna design plays an important role in terms of the bandwidth of the terahertz detectors. That's what she determined during her PhD. So then what she does is that she tries to put another set of nanowires in the perpendicular to the ones which are at the bottom here, for example. Challenge has been to avoid the contact between the top nanowires and the bottom nanowires. And if they're physically in contact, they short circuit the device and you'll not be able to measure the polarization result terahertz detectors, for example. You can see the close-up of these nanowires, and then afterwards you see the antennas here, the nanowires close-up of this one here. You can see instead of using a single nanowire, she used two nanowires, and then on bottom and then the top here, essentially it looks like a bit of a hash tag structure, for example. Okay. So if you take these nanowires, and so the polarization detector, and then what we are trying to do is that trying to measure the properties of the terahertz metamaterial. She designs a terahertz metamaterial and sends a terahertz pulse through this one. And then this terahertz pulse is interacting with the terahertz metamaterial, and the polarization state of the terahertz pulse changes. And we using our detector, we can measure both X and Y polarizations because these nanowires are in orthogonal direction to each other. So here is a case where the actual device, which is really the terahertz material, which is fabricated, designed and fabricated, and her design shows that theoretically that the X polarization should have this type of transmission, and then the Y polarization you would expect to have this type of transmission. And then our detector shows that you can see that you can measure these ones, and then again X polarization, Y polarization, and very much comparable, indicating that we're able to make use of these ones to get the full terahertz polarization state as well as the amplitude and phase. And these terahertz detectors are also operating at room temperature again. And in fact, this work last year we published in Science, for example. Here, for example. Again, Kunpeng has spent about 3 years to be able to get these ones working with my colleagues at University of Strathclyde and also at the ANU. So now let me move towards nanowire solar cells. And so then why are we interested in nanowire solar cells? It turns out, and nanowire solar cells have got lots of advantages. So then you can see that typically you got a thin film solar cell, you need to create a PN junction. You need to make it thick enough to be able to absorb all the light, so thereby you're not wasting light, for example. Here typically few microns thick also. So now the photocarriers need to migrate or diffuse to large distances to the P-type contact at the top and the bottom, for example. Here. In the case of nanowires, you can make the nanowire as long as you want to absorb all the light, and you can make a lateral PN junction or a core shell PN junction. So that means you'll be able to collect the carriers very efficiently. So that means for the first time, you're able to decouple the absorption pathways and the carrier collection pathways using these nanowire solar cells, for example. They also got intrinsically their anti-reflective properties because light gets trapped in these nanowires. So that means you've got very low reflection losses. That means you don't really need to really put anti-reflection coatings or anything. And more importantly, they also act like light funnels, because of the fact that nanowire has got a high refractive index with respect to the air, and then light falling in between these nanowires also get collected into the nanowire, essentially acting like light concentrators or light funnels. Again, we have gone off and did a lot of FTD simulations of the carrier generation profile, and then looking at what should the height of the nanowire, what should be the diameter of the nanowire, what should the pitch or the distance between the nanowires or so. You can see that the most of the current is generated at the top of the nanowire, indicating that you don't need to make very long nanowires, and about a couple of micron long is sufficient, particularly for indium phosphide or gallium arsenide, for example. And again, we looked at this nanowire diameter and then the diameter to pitch ratio. We can see that the about 150, 160 nanometer diameter is very good from the point of view of creating the maximum amount of current. And then also diameter to pitch ratio should be somewhere around 0.5 or 0.6 or so. You can see the individual plots, which I'm showing you here. Again, the challenge is how to make contacts. And then again, when you take these nanowires and then you fill this with a polymer material, like in this case, PCB and selectively etch this one using plasma etching, put some indium tenoxide contacts at the metal contacts at the bottom. So thereby light can transmit to this indium transparent conducting oxides. You can see the top contact, and you can see the nanowires here at the bottom contact here. Again, to cut the long story short, and so really here is we shine light and look at the light, the efficient, look at the light IV characteristics, and then calculate the power conversion efficiency. And these are some of the highest efficiency solar cells made out of these nanowire solar cells demonstrated by my colleagues at the Technical University of Eindhoven, and then FOM Institute in Memel, and Professor Eric Barker's, Eric Garnett's group. And then they're able to show that we can get excellent efficiency of about 17.8% efficiency or so, which is looking extremely promising. Prior to that, my colleagues at Lund University have demonstrated 13.8% and 15.6% solar cells. So we are working with Professor Laura Hertz's group here, and sort of using polymer like structural polymers like BCB and PDMS. We are trying to replace those polymers with the organic semiconductors like P3HT, PCBM, and G2 or MUHPPV. And then thereby we can make use of best of both worlds of organic semiconductors and inorganic semiconductors. And the nice thing with these ones is that you can peel these things off very nicely because of the fact that they're embedded in organic semiconductor polymer. So that means you can create nanowire flexible solar cells. In the future, in principle, you should be able to have the solar cells which are sitting on your backpack and be able to really charge your electronic devices while you're walking around in the sun, for example. So that's what we are moving towards in collaboration with my colleagues at Oxford University. So now let me finish off with the last two topics. And so photoelectrochemical water splitting. The energy is a major issue. And then of course, climate change and greenhouse gas emissions. And then, while solar cells are very good, but one of the challenges with solar cells is that you cannot use them for during nighttime, for example. Hydrogen is seen as a clean energy source and a transportable energy source. And we are really again trying to make use of these nanowires for a photoelectrochemical water splitting. You take a semiconductor, which can act like a photoanode, and you shine light and excite the electrons from the valence band to the conduction band, and then the holes generated end up really doing essentially what they're doing is that oxidizing water, you generate protons and then water and oxygen, for example, here. And the electrons are coming here and then combining with the protons here, reducing the protons to be able to generate hydrogen at this cathode region here, for example. This work is really driven by my colleagues, Dr. Shivakar Turi and Professor Botan, for example. So we've looked at a wide variety of materials, which are the best materials. In fact, there's a plot which I borrowed from Professor Zeti and me, my colleague from Michigan, collaborator from Michigan University. And they've looked at what type of various materials we can make use of. One of the requirements is, and then the band gap of the semiconductor is such that the redox potentials of water should be within the band gap of the semiconductor, for example, here. So you can see that the gallium nitride is very good because you can see the redox potentials of water are in the band gap here. Titanium oxide is very good, but these materials have got a band gap about 3 or 3.4. That means they're only absorbing the UV light. They're transparent to visible light, for example, here. So that means, these are not really optimum for this purpose. But indium nitride, which is only really straddling this particular potential here, but not the second one here, for example. So that means, only oxidation potential, but not the reduction potential, for example. But if you choose indium gallium nitride with the right combination, you can have the band gap, which is really able to absorb the visible light and also able to straddle these redox potentials, for example, here, for example. Okay. So now based on these ones, and we will be exploring the gallium nitride is the work of my student and Dr. Reddy, and also that another colleague, Dr. Liu, also is involved in this one. He's made this gallium nitride nanowires by using top-down etching approach, and looked at shine the light and then look at these ones photocurrent density as a function of the over potential. It turns out that these particular structures are not very stable, though normally very difficult to etch gallium nitride. Why we had to coat this cobalt oxide on top of this one so that it can protect this surface of gallium nitride, because photooxidation is a major issue, and so that we'll be able to show that it can get very stable structures also. And most recently, we've demonstrated 17% efficient standalone solar water splitting system using perovskites and putting on top of silicon, and using the perovskites as essentially as the solar cell, and as powering this particular device, and silicon as a photoelectrode, for example, here, photocathode here, for example. And then this was identified as one of the breakthroughs by the Cool Earth Forum in Japan as one of the top 10 innovations last year or so, showing that we can be able to really develop these technologies for that. But this of course is the silicon tandem observer, which is slightly different technology. Now let me finish off with the last topic of brain repair. So you can see that all of us have got 80 billion neurons, and these 80 billion plus neurons, and then these neurons form into these neuronal networks here. This is work led by my young colleague, Dr. Vinay Gautam, who did PhD from Jawaharlal Nehru Center, Bangalore. So she worked in my group for some time. Now she's lectured in biomedical engineering at Monash University in Melbourne. Melbourne University in Melbourne. Yeah. So what happens whenever you get a brain damage due to accident or one thing or the other, you lose some of these, you break this neuronal network, and you lose some of the functions. You'll not be able to move or talk or eat, or one problem or the other. We asked ourselves, can we create a neural patch and be able to make the connections back so that we can be able to provide the functions back to people, those who got neurological disorders, for example. Again, Vinny spent about 3 years in optimizing various things. And then you see, here's a case where she's growing this neuron on top of these indium phosphide nanowires. You can see the close-up of these ones here. So this is a cell body soma here. And then these dendrites and axons are really growing long distances. Also, these following these patterns beautifully here. There's a square or rectangular patterns of these ones here, for example. You can see some of these dendrites which are coming out of these axons, and again, they're following these patterns beautifully here as well. Instead of using a single neuronal cell, and what will happen if you put multiple neuronal cells? So you can see these green ones are these neuronal cells, and this box is the one where the indium phosphide nanowires are. And you can see these neurites and then axons are really following these patterns beautifully here. If the neurons are grown on indium phosphide flat surfaces, and you see these axons are randomly making connections, there's no patterning, but whereas in this case, there's a nice pattern has been generated here. So what Vinny does is that she puts some calcium dye and does something called calcium imaging. So what happens is the fluorescent intensity of this calcium dye is dependent on the amount of calcium ions which are available. As and when these neurons are firing action potentials, ion channels are opened up, calcium ions are passing through, and then the concentration of the calcium ions are changing. So that means she's able to see this, takes a video of these ones and the change in fluorescence intensity, and then as a function of time, and correlate these ones. If this neuron is firing happening to what's this neuron, what's happening to this neuron and this neuron, these astrocytes or so. She compares these neuronal networks which are grown on nanowires with respect to the neurons which are grown on plain glass substrates, which typically neuroscientists use. Here is a case where she looks at these ones which are the glass, for example, change in fluorescence intensity as a function of the time. This means as and when this is happening, this is where the action potentials have been fired here, for example. So you can see that they are all randomly firing as and when the neurons are grown on glass substrates, and you see very little correlation here, for example. But again, here in this case, when these neurons are grown on indium phosphide nanowires, you can see change in fluorescence as a function of time, and you can see all are really firing at the same time. You see excellent correlation, indicating that there's some sort of a synchronized and correlated activity is taking place. And this work we published this work about 4 years back or so. About 3 years back, when Vinny has presented this work at a neuroscience conference, and neuroscientists were asking what neurons you're using. Then she said she's using the rat neurons, and they said, why are you wasting your time? How about using human neurons? So now we got a funding from Dementia Australia Research Foundation and the Bilbao Foundation to be able to really use of the stem cells from the Alzheimer's patients and stem cells from the healthy people, and then trying to using the CRISPR technology and then be able to make these organoids or the mini brains, and with and without microglia, and then using microelectrode, nanoelectrode analysis, and calcium imaging to be able to understand the signaling behavior differences between the Alzheimer's patient neurons and then the healthy people, and then applying the deep neural networks and then the artificial intelligence to be able to analyze the data so that it can differentiate signals. Also, instead of using microelectrode analysis, and we're developing also nanoelectrodes, so thereby you're able to measure the single neuronal cell the information than microelectrode arrays, which are measuring the signals average of the multiple neuron signaling also. This is really an exciting project, which I'm really enjoying. And then working with my colleagues from University of Melbourne and neurobiologists, stem cell biologists, and also some colleagues at Monash University and Wollongong University and ANU, and also that the microglia experts, and also nanotechnologies, and also the artificial intelligence or computer scientists. Really, it's an exciting multidisciplinary project, which hopefully will be able to help be able to better understand the Alzheimer's disease, and with the hope that we'll be able to help the patients. For example, you can start introducing the new drugs and then measure neuronal signaling and then see which drugs are most effective, for example. So that's what we want to include in the future. With that, let's conclude. And the nanowires open up opportunities for manipulation of light matter interaction at the nanoscale, developing a new class of lasers and LEDs and terahertz detectors. I didn't have time to talk about modulators, terahertz modulators, and again, we published this work, and you can look up. And also integration of optoelectronic devices on various platforms, and using nanowires for solar cells and PEC water splitting, and engineering the growth of the neuronal networks. So really, it's really an exciting time for us, and still there's a lot to do, though we've been working in this area for about 15 years or so now. Let me finish off with the some information. As it's been mentioned, that I'm currently serving as the editor-in-chief of the Applied Physics Reviews, and and if there are any major breakthroughs in your original research, we're accepting both reviews as well as original research. In fact, I forgot to update this one. Our impact factor is more than 19 now, 19.162. And please think of our journal. And also Center of Excellence, and once in a while they start advertising for PhD positions and postdocs. Please keep an eye on this website. And also my wife and Vidya and I have started an endowment to really support students and young physicists from the developing countries to come and visit ANU Physics during their summer break or so, to be able to really access the state-of-the-art facilities and also interact and develop their networks. And typically these are open in December time. And also based on the success of that one, Future Research Talent Program has also been opened up by the ANU. And in fact, many students from IIT Bombay have come and then spent some time at the ANU, but unfortunately due to COVID, we're not able to really offer anything last year or this year. And we just have to wait and see how things will evolve the next year. So at least keep an eye on and pass it on to the people, those who really want to get an opportunity to do some internship or so. With that, I want to thank you for your attention. I'm more than happy to answer any questions you may have.
Yeah, thank you, Professor Chennupati Jagadish, for interesting talk on nanowire physics and nanocavity made of the group 35 semiconductor elements. Now we are moving to the QA sessions. We have a couple of questions in the QA box. So I'm addressing the first question is, what is the key difference in vertical or horizontal nanowire?
So that normally most of the nanowires which you are growing are in the vertical direction, and you can in principle also grow the horizontal nanowires as well if you're using the right kind of substrate and other things. So the light interaction will be quite different. It's a vertical nanowire or the horizontal nanowire, for example. Say, for example, if I'm making a vertical nanowire and if light extraction becomes much more efficient, for example, because of the fact that it's essentially it acts like ordered patterns of these nanowires can act like a photonic crystal, for example. Sometimes we use it to remove the nanowires which are grown from the substrate where it's sitting in the vertical direction and transfer them into a glass substrate and be able to make contacts and other things. Sometimes we make use of these ones. For example, if I want to make more efficient solar cells, keeping them vertically is good because you're able to use this light funneling effects and all these things. So it all depends on the what applications you have. And then you choose either vertical or horizontal nanowires.
Okay. Next question is, how you fabricated branched nanowire? Explain briefly. Fabrication wise, okay. It seems very tough to design branch in vertical nanowire.
Yeah, branch nanowires is very interesting. And what we have done in the case is that we have really grown this indium phosphide nanowire, for example, And then what we have done is that we have taken out from the MOCVD reactor and then coated, small diameter gold nanoparticles on top of that one, put it back into the MOCVD reactor, and then essentially these gold nanoparticles which are on the stem of this nanowire acts like a nucleation site, and you can create these nano trees, for example, in the case when I'm showing the nano tree, for example. And the hope is that the different size of these nano branches end up absorbing different parts of this solar spectrum, because the smaller the branch size, they can end up quantum confinement effects. That means it changes the band gap, and we can get the absorption of the different parts of solar spectrum. That's one of the reasons that we will explore that one. The second case, in the case of when we are growing this indium arsenide, it turns out the surface energy difference between the gallium arsenide or indium arsenide is such that, and generally these gold prefers to be in contact with the gallium arsenide, not with indium arsenide. So then it prefers to really grow out of that one. So that's why I end up creating this branch nanowires or so sort of. So again, depends on the particular application or particular shape. You need to choose the right conditions in order to be able to do that one. Again, Dr. Mohan Palladgu, and who is in the US now, and then he is in one of the industries in Ohio. And then he has really spent a lot of time in really as part of his PhD at University of Queensland, working with us jointly at ANU. And then he has really grown these, these branch nanowires of indium arsenide on top of gallium arsenide. It's a non-trivial process, you're right, but really try to understand the physics behind the growth mechanisms, and then be able to really use them for applications also. So that's why initially we focused on really controlling the shape of the nanowires and the defect structures, and then wide variety of the composition of the nanowires also. Once if you're satisfied, we're able to get good quality structures, and then started moving towards devices. For example, if your nanowires are defective, then again, you're not be able to get a good quality devices as well. And so that's why you need to really focus on both material side and the physics side, as well as also device technology side. And all three of them need to come into picture. And electronic engineering, the nanofabrication, and then understanding of the properties of the materials, and designing using physics, for example, and the materials growth and other things as well. So that's why that having that combination really helps me able to really do all things in a good way.
Okay, moving to next question. What specialty of ring cavity for lasing? Can we use other cavity like this or etc.?
Okay, this depends on, basically what happens if if you got a ring cavity, what happens if the light is really rotating within this one of the spring gallery modes. And then what you could do is that you can be able to really put a waveguide and another, say, nanostructure, nanowire type structure, for example, or essentially a state waveguide, and be able to couple the light to outside world, to whether it is an optical fiber or anything of that sort. So that really gives us lots of flexibility. You can have the multiple rings which are resonating at different wavelengths, for example. So that means you'll be able to send multi-wavelength light through this particular waveguide, and be able to really couple that one to optical fiber and be able to send that information. So that's why ring resonators are really very much of interest. And also people are using the ring resonators and using nonlinear optical properties of this ring material. And people are also able to create these frequency cones. And that again can also, with this particular distance between them, they could also be used for a multi-wavelength devices for sensing and a range of applications as well.
Sir, I have one question in additions, like in your ring resonator lasing, you explain like how you extract the light emissions. I didn't see any waveguide coupled to that ring cavity.
Okay, so I agree that I think ideally you want to have a waveguide and be able to couple the light out. But in this case, what you do is that you're doing all these things in an optical microscope. And then you'll be able to really, whatever the light which is scattering out, means otherwise, if you want to call it, then that is the evanescent waves are sufficient to be able to really be able to measure the intensity profile from the top. Otherwise, if you really want to couple to somewhere else, you certainly need to have a waveguide. You're right. Yeah.
Okay. Next question. What's your thought in thinking nanowire made of TMDC material? Is it possible?
Yes, I don't see any reason why it is not possible. And in fact, even if once you make the TMDCs and then be able to pattern them into nanowires as well, and then study their properties, and then the only thing which you need to think about is what type of surface states which you're really creating in this process, and then how they're going to play an important role. And so people have been talking about, and I think I haven't really looked at the literature, but certainly people have been using, for example, perovskites. and which is another hot topic. And then people are really using nanowires or perovskites for making LEDs and lasers and other things as well. And in principle, I don't see any reason why we cannot make use of these TMDCs, and potentially it can also be used for topological photonics applications and other things as well.
Okay. How smallest nanowire laser is made in your group?
So the smallest lasers which we have, depends on the small in which dimensions, and depends on the diameter or the length. The lengthwise we made the indium phosphide nanowires, which are as small as 2 microns or so. In terms of the diameter, typically they're about 250 nanometers or so. As I mentioned, that if you go to smaller diameters, you're creating more losses. So that means the threshold power really goes up. That means you're really creating a lot of heat, and that means then it pulls the gain peak also down. So then they're not as efficient. So that's why you need to choose the right diameter. That's where the simulations really play an important role as well.
Okay, in vertical wise, how big?
So the length you're talking about, is that right?
Yeah, length.
Lengthwise is about 2 microns or so. By the way, that whenever we are really trying to make this nanowire lasers, and you always transfer them onto a glass substrate because of the fact that they are, you end up having, the mirrors at both ends because of the refractive index difference. But whenever you want to make a nanowire lasers which are sitting vertically, the major problem there is that the refractive index difference between the substrate and then the nanowire is the same. There's no difference, because if I'm using indium phosphide and then indium phosphide nanowire, for example. So what we end up doing is that we try to really make this silicon dioxide, which is really make it a little bit thicker. Then what happens is that as in the whole, the nanowire is growing, and then lateral growth also starts taking place. And then the reflectance or reflectivity at that interface also increases, and that's how we can make these vertically emitting nanowire lasers.
Okay, so we have
and the ones which I'm talking about, these 2 microns are the horizontally lying on a glass substrate.
Okay, so sir, we have a couple of more questions. I hope you don't mind to take.
No problem at all. Keep going.
Okay, so next is what's your view in 2D material TMDC integrated on nanowire?
Oh, that will be very interesting. In fact, it's interesting you asked that question. In fact, we are working with my colleagues at RMIT University, where and you know that some of the TMDCs are very good P-type materials, and we are trying to really put those TMDCs as a P-type contact on these indium phosphide nanowires, and then see we'll be able to really get electrical inducted lasers or not. So there's a lot of potential of combining nanowires with TMDCs as well. Absolutely. And by the way, on that note, we have been working on TMDCs, particularly hexagonal boron nitride, which is a larger band gap material, which is also good for UV electronics. And most recently, we demonstrated, in fact, single photon sources using this, the defects, I think, carbon impurity can act like a visible single photon emitters in the hexagonal boron nitride or so. So we published such work, I think, earlier this year in Nature Materials, also along with my colleague, Professor Jagadish group at the University of Technology, Sydney. Yeah. It is possible to combine both of them. In fact, we are working on it.
Okay, so in ring resonator, why ring shape is a piecewise made of a small rectangle instead of a smooth conventional ring? Is why?
Okay. Ideally, we'd like to have them as really smooth structures, but what happens is that crystals, like to form into these facets. Because the crystals, if you keep on growing, crystals like to be in the low energy facets, and that's why they end up having this faceted structure. So in fact, the faceting structure is not ideal, because it's better to have the smooth structure, because smooth structures have got a higher Q, but then the gain is sufficient enough in these structures to be able to really get a good lasing as well.
Okay. Next question. Do you work on quantum dot based nanowire physics?
Yes, we do work on them. In fact, we are using the quantum dots to really try to look at the single photon emission using these nanowires within which we are putting the quantum dots also. And I think recently we published a paper on quantum disk or quantum dots and nanowires as well. Published, or otherwise it's maybe still in the final revisions or so sort of thing. So please be on the lookout. Essentially, we want, as part of our center of excellence, TMOS center of excellence, and we want to really make use of incorporate quantum dots within the nanowire as well as ring resonators, and then be able to use them for single photon emission as well.
Okay, moving to next question. What are the simulation software do you use in nanowire or other cavity designing?
So mostly, it's again depends on the students. The different students have got different interests, and we typically use mostly numerical. And some students also like to use COMSOL, and then it's depending on which student is interested in what, and I allow them to go and then use them, because it's easier to really give them what they want, so thereby they enjoy what they're doing, and hopefully they'll be able to also produce good results. So that's why we got both the packages, and we use depending on different students are different, but most of these nanowire lasers have been done using numerical, and solar cells are also done using numerical.
Okay. What do you think about nanowire made of polymer material?
Polymer materials, people have been working on these things, as I was mentioning to you, perovskites people have been exploring. A lot of people are also exploring polymer materials for using polymer materials also in the nanowire form as well for various optical applications. Absolutely.
Okay. When you're using vertical
only thing is that polymer, excuse me, once just as extension of that one, polymer materials have got a low refractive index with respect to the 3-5 semiconductors or silicon or so. So that means the light confinement may not be as high, but still it is possible to use them for various applications.
Okay. Moving to next question. When you're using vertical nanowire of such a high aspect ratio during the device fabrication, do you find bending of some nanowires, and how do you avoid bending?
It's a good question as well. So basically what happens is that that's again, that it all depends on the diameter of the nanowires. In fact, we have studied the mechanical properties of these nanowires, and whenever the nanowires are very thin, what happens is that you can really bend them, and they can accommodate strain as much as 10%, which is normally is not possible in the bulk material, for example, sort of thing. And so then, but whereas if you go to larger diameters, then they are stiff enough, and then they really don't bend much. And it turns out that when we were doing some scanning electron microscope imaging of the nanowires, and they used to really, they come together because of the electrostatic charging leading to them to bring them together and all things. And again, we published those papers, which is done jointly with my colleagues at Professor Liao's group at Shizhao Liao's group at the University of Sydney, for example.
Okay, so next we'll take 2 more questions, then we'll go for end of sessions. Question is, in vertical nanowire solar cell, the junction was along horizontal, while carrier transport shall happen in vertical. Could you please explain carrier transport in brief?
Okay, so the ones which I've shown you till now, most of the nanowire solar cells are made out of this axial PN junction. So one part is acting like N-type and one part is acting like P-type. But actually that is not ideal, but that's only one which people have reported, including us, for example. But then what we're talking about is that, means when you got these core shell nanowires of the PN junction, so then what happens is that the built-in electric field of the PN junction is the one which is really removing these carriers quickly outside this recombination region of the depletion region, for example. So then the carriers can transport along the length of the nanowire and be collected from the top and the bottom. But the most of the recombination takes place when the carriers are within that recombination region. So that's what we are really trying to really take it out as quickly as possible, because the nanowire diameter is only 200 nanometers or so, and at the most 300. And that means, you'll be able to efficiently remove, separate these carriers in the lateral direction, horizontal direction, and then be able to transport vertically.
Okay, so last question of the session is, what would be the basic difference between N-polar gallium nitride and G-polar gallium nitride?
So basically the polarity of the gallium nitride also plays an important role in terms of the electric field, for example, built-in electric field, because of the fact that the polarization fields will be different. And again, depends on what applications you got. You have to really choose the right kind of polarity as well. And in fact, I got a student who is really working on now, and who is looking at the Sona Chandadikari, who came from CCRI Pilani, and then he has been working on making these aluminum gallium nitride nanowires and for UV optoelectronics. And again, in this case, he has been really looking at how the polarity has been affected by the growth conditions or so. And we can make either gallium polar or the nitrogen polar structures, and then the properties change quite significantly.
Okay, so thank you, sir. Like QA session is almost done, and it's explained all the questions. So now ending session. So let's thank the speaker for the wonderful talk on the optoelectronics, especially the nanowire physics. And thank you, sir, for accepting our invitation and joining us today to make the Teachers' Day full. And happy Teachers' Day. And in future, we'll also collaborate for the other talks. Yeah, thank you. Thank you for joining today.
Yeah, I'm always there to help and support you guys. And anytime if you want me to come and have a chat. In fact, I also give these talks on failures are pathway to success, and then really sharing people about the failures. Sometimes, you may be brilliant, but every time there's a failure, you get depressed and you're worried about it. But in research, failures are really part of life. And I mean, all the nice results which I've shown you is after a lot of hard work by many students at postdocs, and sometimes they might have spent 2 years or 3 years in order to be able to get those beautiful results. And so my advice to all of you is that believe in yourselves, and then a lot of good things are possible in life. And good luck to all of you. Thanks again for inviting me to participate in this Your LAMP talk series.
Thank you, sir. Thank you for suggestion and support. Okay. Thank you, sir. Bye. Have a good day.
Thank you. Bye. Bye-bye. Bye-bye. You too. Thank you. Bye. Okay. Bye, Kishore. Good luck.
Bye. Bye, sir.